Sorry, I will start the record as well. So there have been a lot of questions on the channel 3 atmospheric and circumstellar dust formation, structure and dust formation. And so please, now it's the moment that if you have a question, raise your hand. I will let you talk. But let me start with the questions that are on Slack. So Stefan asked, concerning the question, does every star have a companion, which seems to be connected to the work on DESIN and others 2020. I would like to know if the sample of DESIN 2020 has been selected to explicitly target strong binary candidates or free of such bias. So I think this is a question for Thaisa, perhaps.
Yeah, sure. So the sample was not specifically chosen for looking for binaries with ALMA. It was chosen to cover a broad range of mass loss rates, pulsation types, so Mira semi-regular, and then the stellar angular size was also taken into account. And it's also a fairly small sample, it's only 17 stars. So of course it's not complete. So we weren't looking for binaries. There a couple of stars were known to be binaries, but we were just looking for a broad range of stars.
Thank you. Roberto Ortiz said just a comment about whether a companion shapes the envelope of a particular star. Check if it has a far UV counterpart. The chromosphere of an AGB star emits in the near ultraviolet, but in the far UV domain, its flux should be negligible. Check it out at Ortiz and Guerrero 2016. And I have to add that also there is another work on this by Rodolfo Montes in 2018, I believe. Yeah, do you have any comments on this, Marcus or Thaisa or anybody else? Well, I guess this was just a comment. So, oh, Jaakko.
Well, just to follow up on that, I guess if we are going to monitor, we want to monitor close binaries and see what happens to the wind as the companion goes around. I mean, this is something that's done, has been done a lot for massive X-ray binaries in particular in the past, and also using the companion as a probe of the local wind conditions, which you've both showed can be seen. So that's just in addition to other reasons for monitoring, essentially.
Okay. Yeah, great point. Thanks, Jaakko. So another very interesting question was raised by Jaakko: how important are planets? To which Claudia Palladini follow up with, how do you know it's a planet and not a bulk of dust? And also, do planets form or do planets get nicked, like a Jupiter planet losing its envelope because of the interaction with the stellar wind? Claire comment with great question. I also found it puzzling that different works showed in the past that planets alone aren't enough to shape a planetary nebulae. So how big a planet, how distant? Thaisa, you added something on this. Claudia and Claire and Jaakko, if anybody wants to comment on this, please feel free to raise your hand. And yeah, Thaisa, do you want to voice your comment so everybody?
Yeah, sure. So some people in my research group, but I stress not me personally, have been working on these hydrodynamic simulations to see when planets can shape the wind. And the preliminary results seem to be that there have to be a fairly large planet, so Jupiter or higher mass, and fairly close to the star. And these aren't yet looking at how that situation comes to be. So I can't really comment on that. But I think these others maybe have some interesting comments.
Sure. Patricia and Claudia, I saw that you want to speak. Please go ahead and unmute yourself.
Can you hear me?
Yes.
I would just point to the 5-minute recording by Igor Szynski on planets accreting mass from the mass-losing stars and causing the long secondary periods that we see in the LMC. It's something I'd intended to mention in my talk on Friday, but I thought that was quite an impressive demonstration about how planets, by accreting mass that's actually being lost from the stars, can have quite a significant influence. Thank you.
Thank you. Yes, great pointing at that talk. I have also seen it, and it's impressive. Claudia, do you want to add anything?
Yeah, I wanted to ask how much the fact that most of the models we are using are modeling just the wind and not the full star that is below. Does it bias our results? Like, does it mean that we are blind to these planets that are within 10 AU? What does it happen to those ones?
Yeah, great point. Well, I think I think one of the points concerning this problem is that also I believe these planets are enshrouded at this stage of the star evolution, and so to solve them, I guess there have been quite some works studying how how you would need to which resolution you will need to solve them, because they are really enshrouded in dust. Well, not only resolution, but like how would you resolve them? And so also there have been also some other works pointing at what happened if the wind of the star just pushes away the planet, or if it's enshrouded in the mass loss. So I will check back this work and post it. But Silke, you added something to this discussion. Do you want to voice your comment? Well, I mean, if you're interested, there is a thread on this. And okay, so let's move on to the next question. Phil Massey asks, what are the typical uncertainties in log L and effective temperature in the interferometric determination for red supergiants? Thanks.
Yes, I showed the table at some point. In log L, it's about 0.1 to 0.4, and the error is dominated by the distance, with error on the distance. And on TF, it's typically a few hundred Kelvin, and here the error is dominated by the bolometric flux, by the error of the bolometric flux. So we could get better with complementary data. At some point, actually, we did get simultaneous photometry at the SAO, JHKL, with Patricia Whitelock. So such auxiliary observations could help to be more precise here. Gaia, unfortunately, doesn't help yet, but maybe it will for the distances.
Yeah, thank you, Marcus. Yeah, I also had a comment on this, that, it's pretty clear from your works that, and from other works, that we need really time series observations to probe the temporal variation of these stars. So I was wondering, as a community, what effort can we do toward this? And if perhaps, Jaakko, if you're taking note for our white paper, if we can also, raise this to the larger community, and some, of course, Tomek said a multiple wavelength simultaneously, and Joseph comment that this point has been brought since the 80s, and it seems that the only solution is a dedicated telescope. So yeah, we can call it the multi-wavelength, extremely large telescope. Well, that's already part of the name, is already taken, so you have to invent a new one, Joseph. Ming Yang said there are quite a lot of optical time series data from DECAM, PanStar, and SkyMapper. Ming, do you want to tell us more about this? Okay. I don't see him raising the hand, so I think we can just move on to the next question. Ben Davis thanks, Marcos, for your talk. As you say, the hydrostatic model atmosphere used to model red supergiants don't include the wind. If you stick one on with the typical mass loss, you can explain the specially extended molecular emission, as well as make the Taiyo bands stronger at fixed effective temperatures. Marcus, do you want to comment on this?
Yes, no, this is certainly very interesting. I know, Ben, that you are working on this, and in absence of fully consistent models that can explain the levitation of the atmosphere, I think it's the best way to do such semi-empirical models to add the wind. Yes.
Yeah, and Thaisa, also, if you want to comment, please feel free to unmute yourself, or anybody else, if you have further comments or questions, please raise your hand, and we will let you talk. Okay, Janet Bowie investigate archives. There are observations in the Spitzer archive for multiple epochs. I know also that there were publications back in the 2000s, but we'll need to look them up. All right, yes, if you can include references to this, that would be great, thanks. Yes, Jaakko point out to Kriek Ekman work, and Stefan put the link to her profile, but it's a bit out of context. So Jaakko, do you want to tell us more about this?
Sorry, I was just following up on another thread, and with all the parallel threads in the Slack channel, it becomes quite a tree. Were you asking about the comment about the non-sphericity?
No, you just write Kriek Ekman. I guess you wanted to.
Oh yeah, Kriek Ekman. Yeah. I believe she did mid-infrared spectroscopic monitoring, really doing pioneering work in the days when nobody expects it's possible. It's surprising how little came off that, I think, but it was quite a brave effort. I remember I was young too then.
Okay.
Now the point I was making, actually, I was replying to the Mars. So there was a suggestion: how do you know it's a planet, or how do you know it's a dust clump? But obviously, it's the Mars, which you may or may not be able to get a handle on. But if you see certain dynamical effects that suggest the action of gravity, then you might imply a planet. And if you don't, then you might imply a dust clump. I mean, we can learn a lot from how people observe these kinds of things in protoplanetary disk, of course. Because on the one hand, a lot of attention has shifted to that field, but we should also try to benefit from what they find out, both in terms of techniques as well as physics that goes on, because we see so many parallels. Now, you've all shown things that we often associate with protoplanetary stages, but we see them in the post main sequence evolution. And in that regard, decades ago already, especially Hans van Winkel, for instance, they looked at post-HEB stars, and they suggested that it might be possible to form planets in the disks around post-HEB stars. I wonder what has come of that idea.
You mean to form planets, or to have the planet like?
Yes, at the time the idea was that they might actually be able to form.
Okay, can you post the reference on Slack so everybody?
I don't have it in my head, but basically 20 years ago in the ISO time.
Okay, thanks.
Hans van Winkel worked on it.
Okay, then Janet also added that there were published UKIRT data as well. Thanks. And Jaakko added that we see planetary debris falling onto white dwarfs, and yeah, what he just added. So Dieter Engels said that none of the SIO Maser monitoring program of AGB stars probing the shell at about 5 stellar radii have shown velocity variation which could be attributed to binary motion. And Tomek replied, Araquari did show an orbital motion in SIO lines. Marcus, I know you have done quite a few work on Araquari. You want to add anything?
Not specifically, but just to say for the companions, I think it's two different discussions really. So companions definitely shapes the wind at larger radii, as Thaisa has shown in these beautiful ALMA images. But whether they really influence the onset of the mass loss close to the stellar surface, I think it's a different question. So I think they would have to be very close to the primary to be able to have an impact on the mass loss, on the onset of the mass loss itself. So I think we have to differentiate the effect on the onset of the mass loss and then the shaping at larger radii. And indeed, there may not be many companions at these very short distances that could affect the mass loss itself. Like also for the R Sculptoris, which I've shown, we know there is this companion which makes this beautiful spiral, but the structure that we see very close to the star, we came to the conclusion that this has nothing to do with the known companion.
Okay, thanks. And Jaakko actually asked if do we only get masers if the atmosphere is not disturbed by a companion, and Dieter Engels added that there are counterexamples. So Dieter, if you want to speak, please raise your hand so I can unmute, or I can also allow to talk. And Jaakko, if you want to add anything, otherwise I will just continue.
I only want to say, if you want to monitor for binary motion, you should consider to use SIO masers to find out if close to the star there is evidence for binary motion. So even not only using optical spectroscopy, also the radio masers can be used for that purpose. Thanks.
Yeah, great point. Thanks. Jaakko also follow up saying that if a red supergiant is not spherical, do we get the right luminosity and effective temperature? Yeah, does anybody want to comment on this?
No, I think we don't, but the question is how aspherical can it be? I think there was an interesting paper from Keiichi Onaka some years ago on the star in the LMC, was it G64 also, which was aspherical, and then he could revise effective temperature and luminosity. Indeed. So
yeah, I have allowed
KG. And we know, I mean, then we can get rid of this. But I mean, as long as we haven't resolved them and don't know if they are spherical or not, there might be an effect.
Same with convection cells, large convection cells, if they cover a large part of the surface. I mean, this is one of the things people have been thinking about in interpreting Betelgeuse's behavior.
The whole concept of effective temperature is probably questionable because you would have different temperatures in different areas of the star, like what we assume for Betelgeuse dimming.
KG, do you want to add anything, or anybody else?
Hello?
Yes.
No, I think the case Max mentioned is WRTG64, the very bright receiver joint, and the LMC is a very, I would say it's a very special particular example because it has a very, it's from the SED, it's clear that it has something, it's not completely, it's not spherical, not even approximately or globally spherical. But for other stars, I would say there are some inhomogeneities of the surface, but I still feel that the average effective temperature and luminosity represent the position of the stars on the HR diagram.
Yeah, thank you. Thank you, Keiji. So we have 7 minutes left and a few more questions. So Marcelo said, you mentioned the Jaco, you mentioned the possibility of planet formation in post-AGB disks, but I failed to get the names of the author you were mentioning. Can you write them down? Oh, Hans van Wickel. Okay, this has been settled actually. So Tomek raised a very interesting question. So which of the outline problem will the speakers prioritize for the upcoming decade? Which ones are within our reach? Do we need more theoretical work or more observational? And yeah, so I will give the speaker the word.
I think both, but I think to start with more theoretical work to understand what we've already seen. There were a lot of unanswered questions, right, as I showed in my talk. And I think primarily we need theory to understand them. And then we can observe more, confirm with observations, perhaps discover more things that we need to explain further down the track.
Yeah, I agree. I think we need more theoretical work to understand the onset of the mass loss. And then we need observations along the process to constrain the models.
Yeah, I think they quite work in synchronous.
And I think, I mean, it would be good to bring together everything we know about the different red giants and supergiants, from red giants, AGB stars, Mairas. So to bring together which physical explanations we have for each of them and see how relevant they may also be for other luminosities or other parts.
Yeah, thank you. And Tomek, do you want to add anything to this? Do you have your own? I see. Sorry, Claudia. Yes, please. Go ahead.
Yeah, I wanted to ask to Thaisa. Sorry if I misspelled your name. So you say that you need more theory, so more theoretical work. What is it missing to bring you to do this theoretical work? Because for the observation, we have to plan ahead and so on. So to ask for the time, go through the TAC. But from the theoretical part, what is it that you are missing to reach the understanding? I know it's an old-fashioned question, maybe, but yeah, thank you.
I mean, I think one of the issues holding back theoretical work in the past was computational limitations, which of course continue to improve. So perhaps that's something that people, now can start working on. As I mentioned, there are people in our group at Leuven working on hydrodynamic simulations. There are people working on chemical modeling, but there's still a little bit to go between reconciling like observations of molecular distributions with chemical predictions. So that's still ongoing work. I think we'll hear more about that later in the week. So I'm not suggesting there's no theory happening. I'm just saying there's a lot of unanswered questions still.
Thank you. Yeah.
Can you say a word on that topic?
Yes, please. Yeah, that's why I like.
So I think there are a few problems that are real showstoppers in our field. For instance, the nucleation theory. Many theorists use some nucleation prescriptions, but they are not very well verified by observations or not very well grounded in the microphysics. So I think this is a very serious problem that needs to be solved theoretically. There are things like shock chemistry or circumstellar chemistry that we don't understand. The astrochemistry, that prescription that we have does not have any predicting power. So I see that we have a lot of nice observations. We show all those maps in our papers. They look beautiful, but we don't have real understanding of what is going on there. And I feel that the theory is really behind. We need more theoreticians in the field. Thank you.
Okay, thank you. Jaco, do you want to add a few words? I see your.
Yeah, because we're getting close to the break, but I just wanted to lend some support and visibility to Lauren Harrington's suggestion that the AVSO and in general amateurs are actually quite capable nowadays with their equipment, and they are even doing spectroscopic monitoring. And while they might not be able to do VLTI quality interferometry, but they can do a lot of interesting work that we just don't get to do, or are not even able to do at large telescopes anymore. So just wanted to lend that support so that it doesn't go unnoticed.
Thank you, Jaakko. And Susanne, please go ahead. I see your hand raised.
Thanks. I'm glad to hear that observers are calling for more theory. As many of you know, we have some ongoing work, but this is also stuff that really takes long time to do, in not the least the 3D models. I mean, just the running times for these models are enormous. So yes, there is stuff coming, but it's not yet quite finished. But those of you who were at the Delft conference, for instance, could see that there are now at least grids of HEB star-in-the-box models with lots of stellar parameters for explaining pulsation and convection and so on. The wind models are on their heels, but they are not yet there. We hope that we will soon have something to contribute here.
Thank you. Thank you, Susanne. And yeah, I believe those, theory and observations are always go always hand in hand. And of course, we need observations to contrast theory, and then theory to have a sort of feedback on what we are observing. So I guess we will need to work together as a community. But please feel free to continue the discussion on Slack. We have 0 minutes left, so I will just quickly read what people wrote. Graham Harper asked for the reference, and actually it was the video, so it's there. There is a thread, we need more theory or we need more observations. Feel free to read that. And B-Way actually asked Marcus, is there any mechanism to form carbonaceous dust around red supergiants?
Well, I don't know. They are typically oxygen rich. I don't know if there might be. I remember there was some work on certain type of chemistry that maybe could do carbon dust in oxygen rich cases, but I'm not sure really.
Patricia, please go ahead. And yeah.
Just that I understand, without understanding the details, that you can do this with shock chemistry, likewise forming oxygen-rich molecules in carbon-rich atmospheres.
Thank you. Great. If B-Way, you want to add something, please feel free to speak. Otherwise, I think we are 1 minute later, so not so bad. And we have now half an hour of pause, of break, and we will resume at 2:40 UTC time. So thank you again all for the discussion, and you can continue on Slack, please feel free, and see you all in half an hour, basically. Thank you.